Handling missing data and outliers is one of the most important steps in preparing a dataset. In this lecture, we'll talk about how to spot these issues, why they matter, and the practical ways we can fix or manage them. By the end, you'll know how to deal with incomplete information and unusual values, so your analysis stays reliable and accurate. Missing data is something analysts run into all the time, no matter what field they're working in: finance, healthcare, or research. It can happen for many reasons, like errors in data collection, faulty sensors, human mistakes, or even intentional omissions. Now, there are three main types of missing data. First, missing completely at random, or MCAR. This is when the missing values happen with no pattern at all. They're just random. Second, missing at random, or MAR. Here, the missing values depend on other data that we do have, but not on the missing values themselves. And finally, missing not at random, or MNAR. This is when the reason the data is missing is directly tied to the missing values themselves. Here we're starting with a simple example in Pandas to see how missing data looks in practice. We first import Pandas and NumPy. Then we create a small dataset with 3 columns: A, B, and C. To make this realistic, we intentionally added some missing values using none. When we turn this dictionary into a data frame and print it, you can see the output on the right. Pandas automatically represents missing values as NaN, which stands for not a number. So here, column A is missing a value in the 3rd row, column B is missing 1 in the 1st row, and column C is missing 1 in the 3rd row. This simple example gives us a clear view of how missing data actually appears in a dataset. To quickly check for missing values in a dataset, we can use the Pandas function isNull combined with a sum. What happens here is simple. isNull looks through the data frame and marks every missing value as true. Then, when we apply sum, it counts up how many missing values are in each column. Looking at the output, we can see that column A has 1 missing value, column B also has 1, and column C has 1 as well. This gives us a clear summary of where the gaps in our data are, making it easy to decide how to handle them next. When dealing with missing data, there are 2 main approaches: deletion and imputation. Deletion means we simply remove rows or columns that contain missing values. This works fine when the dataset is large and losing a few rows doesn't affect the overall analysis. On the right side, you can see the code def.drop n a .dash. It drops any row with a missing value. The output shows that only the complete rows remain, in this case, rows 2 and 4. The second approach is imputation, where instead of dropping data, we fill in the gaps using some statistical method. For example, here we use df.fill and a df.mean to replace missing values with the column mean. Looking at the output, you can see that the missing spots have been filled in with average values, so the dataset stays complete without losing any rows. Both methods have their uses, and the choice depends on the size of the dataset and the importance of the missing information. Now let's talk about outliers. Outliers are data points that are very different from the rest of the dataset. They can happen for lots of reasons. Maybe a measurement error, maybe natural variation, or sometimes even rare and extraordinary events. The key thing is that outliers can have a big impact on statistical analysis and machine learning models, so detecting them is really important. There are a few common ways to find outliers. One approach is visualization. Box plots give us a quick way to spot extreme values, while scatter plots highlight points that stand far away from the rest. We also have statistical methods. The Z-score measures how many standard deviations a data point is from the mean. If a value is several standard deviations away, it's likely an outlier. Another approach is the interquartile range, or IQR, which looks at the spread of the data based on quartiles. Any points that fall far outside this range can be flagged as outliers. So overall, whether through charts or statistics, these tools give us a clear way to detect unusual values in a data set. Here we're looking at two common ways to detect outliers, using the Z-score and the interquartile range, or IQR. On the left, we have the Z-score method. We start with a small data set that clearly has one extreme value, 120, while the rest are around 12. The Z-score tells us how many standard deviations each value is from the mean. In the output, most of the values are close to 0, meaning they're near the average. But the last number, 2.2, stands out, showing that 120 is much farther away and likely an outlier. On the right, we're using the IQR method. Here we calculate the first quartile, the third quartile, and then the interquartile range between them. Based on that, we set lower and upper bounds. Any value outside this range is considered an outlier. In this case, the range is about 10.8 to 13.8. Since 120 falls way outside of that range, it's flagged as an outlier. Both methods give us a systematic way to identify unusual values in a dataset. When handling outliers, we generally have three approaches. The first is removal, where we completely exclude the outliers from our dataset. The second is transformation, where we apply mathematical functions like logarithms or square roots to reduce the influence of extreme values. And the third is imputation, where we replace the outliers with something more reasonable, like the mean or the median. In this example, we're showing removal using the Z-score. The code checks each value and keeps it only if the absolute Z-score is less than 2. That means any value that's more than 2 standard deviations away from the mean gets filtered out. Looking at the output, we can see that the extreme value of 120 is now gone, leaving us with the cleaner set of numbers: 10, 12, 12, 13, and 12. This way, the data set better represents the general trend without being skewed by an outlier. Let's finish with a real-world example using stock data. Here we're working with Tesla, and we'll walk through the full process of handling missing values and outliers. First, we download the stock data with Y Finance. Then, to take care of any missing values, we use forward fill. That means if a value is missing, it gets filled with the last available number. Next, we calculate daily returns from the closing prices. After that, we compute Z-scores for those returns to measure how far each return is from the average. Finally, we filter out the extreme outliers by keeping only the returns where the absolute Z-score is less than 3. On the right, you can see part of the cleaned data set. At the top, we have early dates from January 2020, and at the bottom, we see the last few rows from December 2023. Each row now includes the daily return and its Z-score. By removing extreme outliers, we end up with a data set that reflects the usual behavior of Tesla stock without being distorted by rare spikes. Time for a quick hands-on. Pick any data set that interests you: stocks, sales, sensors, anything. Step 1. Check for gaps with isnol.sum and note where values are missing. Step 2. Fix them. Forward fill or fill no with mean or median if that makes sense, or drop a few rows if you have plenty of data. Step 3. Look for outliers. Use Z-scores or the IQR bounds to flag extremes, then decide: remove them, transform them, or cap them. Your goal is a clean table you can trust. When you're done, print a before and after summary so you can see missing counts drop to 0 and extreme values handled. Let's wrap up. You've learned how to spot missing values, quantify them, and either drop or fill them in a sensible way. You've also seen how to detect outliers with Z-scores and IQR and decide whether to remove, transform, or replace them. These steps make your data cleaner, your models more stable, and your conclusions more trustworthy. Take these tools to your own dataset, run a quick before and after check, and you'll immediately see the difference. Great work, and I'll see you in the next lesson.